Good. So as I was saying, lipids are a class, a broad class, including many different types of biologically relevant compounds that are fat soluble as opposed to water soluble. And there's some variation in structures. My focus, once again, is going to be largely on structure, just like I'm largely interested in structure in the heterocycles chapter, largely interested in structure in the nucleic acids chapter, and it'll be the same when we get to the amino acids and proteins chapter, polypeptides, and it will be the same when we get to the carbohydrates chapter. We're going to mainly focus on structure because my feeling is that's probably not what got covered in past biology classes of yours. And what I hope to convince you once again is that even though we may sometimes be talking about really big molecules, we can understand them once we understand the parts they're made up of. So that's going to be a real theme, I think, in these biochem chapters. But biochemical reactions are exactly analogous to a lot of the reactions that we've studied already in this class. I hope to prove that to you as well. I'll try my best. The only differences are, and there are significant differences, but the only differences are we're talking about bigger molecules for one, for sure, bigger molecules. If anything, these biochemical reactions are actually simpler conceptually than some of the ones we've already learned. Like you'll seldom find anything quite as complicated as an electrophilic aromatic substitution, let us say, which we covered in chapter 4. So a lot of these reactions are even simpler. And in fact, a good chunk of biochemical reactions, it seems to me, are acid-base reactions, which are about as simple as it gets. There's a lot of acid-base chemistry in biochemistry. And of course, the third big difference between biochemical reactions and all of the others, which tends to make at times it look kind of like a bunch of magic tricks, is enzymes are involved. And once enzymes are involved, you can have all manner of weird things happening or unexpected things that you wouldn't normally think of seeing in the absence of an enzyme. So, and we're not going to really get into enzyme chemistry specifically. I'm sure you talked about enzymes in your biology class, but I did want to point out those are the main differences between biochemical reactions and the other reactions that we even learn in this semester. And really, all those reactions are in many ways more similar than different. There's a lot of similarities. I can think already of one reaction I'm going to talk about probably in about 5 to 10 minutes that's identical to something we talked about in chapter 3. It is literally the exact same reaction. So I'll be sure to do my best to point that out once we get there. Let's see. Some of the classes of lipids that we're going to talk about include the ones we have here. I want to talk about fats and oils today. I want to talk about waxes. I want to talk about triglycerides, which are also called triacylglycerols. And I'll also try to fill in some of the context behind these. Again, I'll mostly steer clear of biological function, except for maybe some things that I think almost belong in general public interest, but I'm not going to get into heavy detail about biochemical pathways, let us say. But and then also soaps and detergents, in which actually this might not make you happy, I don't know, but there's information in your book that is not in the Chem 227 and Chem 228 book, and I think it's pretty interesting. So I will go over it in some detail because I want to make sure you guys understand it when you read it. But it talks about synthetic detergents, or Syndets, as they're apparently called. And I did not know about this until I had read your book. So, but it is a little bit involved, so I'll take us through that. And honestly, if we can get through this much today, I'll be happy. We have 2 days to cover the chapter. We might end early today. We might end early on Monday. I'm sure, especially on a Friday, no one's going to complain about ending a little early. If we take 50 minutes, we take 50 minutes, but I wouldn't be shocked if we don't. And yet, yes, I know, I do tend to surprise everyone in just how much I can talk. But or really, it's more like 50 minutes isn't a very long time. Anyway, getting back to that which is relevant, let's talk about fats and oils. So basically, Both solid fats and oils are also called fatty acids. And all a fatty acid is would be a very long chain carboxylic acid. So very long chain. The whole molecule could have 16, 18, 20, 24 carbons, let's say. And most of that's going to be in this group R. So fatty acids themselves come in two flavors. Well, that's a bad pun. Two varieties, let's say, which I bet you've heard of both of them, saturated and unsaturated fats. If you've ever read any food labels, and some of you talked about taking nutrition, so I'm sure you talk about all that there. But your solid fats are generally saturated. And these are going to be the ones that are solids at room temperature, by and large. There are some exceptions, but by and large, they're solids at room temperature. And so they will look something like this. I'm not going to necessarily draw an actual existing, well, I think I can maybe, let's see. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Just so you can get an idea of just how big these molecules are. Now, I don't know the name of that one off the top, and I certainly would not expect you to memorize any particular fatty acids. However, I'm sure that's a real existing fatty acid, and I wouldn't be surprised if you can find it in some animal products. Because of course, as you're aware, your saturated fats, the ones that are solid at room temperature, generally come from animal sources. So this is your beef fat, your butter, you know, your Crisco, things like that generally come from animal sources. Meanwhile, oh, I should mention, I think we've used the word saturated before, but the definition of saturated here, it means it's saturated with hydrogen. In other words, you can't put any more hydrogens on any of those carbons. They already have all the hydrogens they can possibly hold on to, except for the carboxylic acid group, of course. But all throughout the rest of the fatty acid chain, in a saturated fat, it means the chain contains the maximum possible amount of hydrogen. So that's what we mean by that. Unsaturated fats, as you would already have guessed and might even be familiar with, I'll just put EX here, for example. Unsaturated fats, these are going to be the ones that are liquids at room temperature. Again, overwhelmingly. And also the ones that come from plant sources, overwhelmingly. There are occasional exceptions. For example, isn't coconut oil sometimes a solid? I've always wondered about that. I don't know why that is, because it comes from a plant, but I've also seen liquid coconut oil. So I'm afraid I'm not that familiar with the details of why that is. But certainly all of your other cooking oils, your peanut oil, your corn oil, your sunflower oil, grapeseed oil, all of these are going to be liquids at room temperature. And you're familiar with these just from going to the supermarket. You've dealt with these on a daily basis. So these are the ones that are going to come from plant sources. And I'll just try to come up with an example of what a typical unsaturated fatty acid might look like. And it's actually rather interesting because it's going to contain carbon-carbon double bonds. That's what makes it unsaturated. It means it's not saturated with hydrogen. It would be possible to break that carbon-carbon double bond and put more hydrogens on. So I don't know, I'm kind of making this up as I go along. I don't promise this is a real existing fatty acid, but it could be. They will always look something like this. And one thing you can tell from my structure here is the carbon-carbon double bonds are always cis in naturally occurring unsaturated fats. And that's strange. I'm hoping that's kind of a surprise to you, because one thing we learned when we covered alkenes in chapter 3 and talked about naming them, cis-trans or E and Z alkenes, one of the things we said is that other things being equal, cis double bonds are less stable than trans double bonds. Yet for some reason, I don't think I can tell you what it is, but for some reason, the unsaturated fatty acids we actually find in natural plant sources will contain cis double bonds, not trans double bonds. And that leads to a few different ideas. Wait a minute. This would be too much. I'm just counting carbons here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Fine. I have my doubt. I just wanted to make it of the same number of carbons as the other ones. Oh, I'm sorry. Yes, which is strange because cis double bonds are less stable than trans double bonds. But in naturally occurring vegetable oils or plant oils, yes, the double bonds are always cis. And I do mean always, no exceptions. So it's quite surprising, but it's true. I should mention that one thing you can do, you can actually convert unsaturated fats to saturated fats fairly easily. All you would need to do is treat them with an excess of hydrogen gas in the presence of some metal catalyst like palladium or platinum or nickel. We talked about that in chapter 3. We said that alkenes can be hydrogenated. And this is the exact same reaction that we talked about in chapter 3. I didn't write down the exact section of chapter 3 that it's in, but you will find that in our chapter on alkene reactions. So this is that same reaction. And you've probably heard of this in the context of hydrogenation of vegetable oils. You might have read food labels, or again, maybe in your nutrition class, gone over the idea of partially hydrogenated vegetable oil or sunflower oil or whatever it might be. And that is exactly what it sounds like. What it means is they maybe don't add an excess of hydrogen. They only add enough hydrogen just to partially hydrogenate all of those double bonds. So some will remain in place and some will be reduced to single bonds. But again, please review that reaction in chapter 3 because it's the exact same reaction here. It literally is the same thing. If you understand that reaction in chapter 3, then you understand this. And it's not bad to go back and review a little bit. It's never bad with there eventually being a final exam to make those connections like that. That will help you to remember the information better, I believe. So, but partially hydrogenated oils have a problem. Well, first of all, why do they do it? And I'm no food scientist, but my understanding is the reason they partially hydrogenate vegetable oils is they're looking for an oil or a fat that has particular properties, that behaves in a certain way, has a particular texture. So they can make, I don't know, the stuff in the middle of a Twinkie, let's say, something like that, so that it has the right texture. And that's all been worked out industrially. But one side of partially hydrogenated vegetable oils, kind of the dark side, is it also leads to some of these double bonds isomerizing from cis to trans. And why it would do that makes sense, because trans is more stable. So you would think there'd be a pathway, and there is, where a cis double bond can become a trans double bond, and then it will want to stay that way because it's more stable. More stable because then you don't have the groups bumping into each other like this, like you do in cis double bonds. So that's a problem. You've probably heard of trans fats. And again, I am neither a medical doctor nor a nutritionist, but I think we're all in general aware that trans fats are bad actors, that I would say people first started getting really interested in trans fats was certainly during my lifetime. I mean, I was young, but you started hearing a lot of talk about them in the 70s and 80s, I would say. So I was really young, but I remember them talking about it. So that's why now they have methods for removing trans fats from the reaction mixture. And that's why you can look at food labels that will say no trans fats in bold letters, because they want to advertise that they've taken out the trans fats. Of course, sometimes they cheat. Sometimes they'll say no trans fats in something like gummy bears that has no fat in it anyway. So sometimes they cheat, but other times it's actually bona fide information, something that would have otherwise maybe had some trans fats, but they've been treated to get rid of the trans fats and still have the properties to their foodstuffs that they wanted to. That at least is my understanding. Like I said, I'm not a food scientist. But I wanted to try to draw these connections to things you might have heard about in daily life. So those are your fatty acids. They can be saturated or unsaturated. Oh, another thing about unsaturated fats. And again, you can correct me if I'm wrong, but my understanding is, of course, unsaturated fats are the ones that are better for you. It's because we have very efficient pathways with which to deal with them that are a little more efficient than with your saturated fats. Again, I'm no biochemist, but that's my understanding. and unsaturated fats. So they're relatively speaking healthy for you. And my understanding is that this is why people in countries like Greece and Italy are living to be 115 years old. They actually have extremely high fat diets, but it's all olive oil. So it's loaded with unsaturated fats that are quite healthy. So, that again, I'm not an expert in that field, but that's my understanding. So much then for fatty acids. Before we go on to triglycerides, though, I want to talk about something related to fatty acids, which is waxes. And you're familiar with beeswax and things like that. And there's other naturally occurring waxes. And they are, generally speaking, long chain esters of long chain fatty acids. So rather than a carboxylic acid, we'd have two R groups, and both are long chains. So, you'd have 20 carbons here and 20 carbons here, maybe some large number of carbons, maybe even more, maybe 30 or 40. But like I said, what I'm expecting you to focus on is exactly this, just how to tell these different structures apart. I would hope that when you're practicing this, I don't promise every single question will be of this type, but you can think of it in terms of matching, which of the following is a wax, which of the following is a triglyceride. This over here is a prostaglandin. This thing here is a terpene, let's say. That would be what I would expect you to do, not memorizing particular ones. I would never say draw prostaglandin F2 alpha. No, certainly not. I don't have them memorized myself. But can you at least tell them apart? That's what I would hope you would be aiming for. And because again, I can't promise I'm going to use it exclusively, but it is a question format that lends itself very well to multiple choice. Right? Which of the following is a prostaglandin, A, B, C, D, E? It just works real well. So good. So I think that's all we really need to say about that. Moving on from this form of fats, there's another one which you've probably heard of called triglycerides. And sure enough, triglycerides are also called triacylglycerols. There you go again. Two different words for the exact same thing. Why it is that way, I don't really know, but it seems to happen a lot in organic chemistry. So triglycerides are closely related to fatty acids. They are the triester, and I have this in the class notes, but triglycerides are triesters of fatty acids, 3 fatty acid molecules with glycerol. So you do need to know what an ester is. We did go over the functional groups earlier in the semester. And it will also be helpful to know what glycerol is. Glycerol can also be called 1,2,3-propane triol. And we haven't officially learned how to name alcohols yet, but I would expect if you sat down and thought about it for a few seconds, you'd find that name makes a lot of sense. It's a 3-carbon molecule with OH groups, 1 on each of the 3 carbons. So glycerol will look something like this. That's glycerol, 1,2,3-propane triol. Glycerol gets a lot of use in consumer products in its own right, for both internal and external use. Glycerol has a number of desirable properties. First of all, it's sweet, so that's a desirable property, certainly in the food industry. Second of all, it's quite benign. Okay, I wouldn't go drinking glycerol by the gallon. That might not be a good idea. But it's quite non-toxic. In reasonable amounts, it's quite benign. And so you'll find glycerol in a lot of candies. I think you'll find glycerol, especially, those hard candies that have like a soft center. They'll put glycerol in the center to keep it soft over time. So it's very non-toxic, and plus has the nice advantage of being sweet. And not only that, I'm not a big expert on any of this, but I think you'll find glycerol various health and beauty products also. I think you can buy like soap with glycerol in it, for which there's a very good reason that we're going to get to, by the way. But you can find other products, probably creams and things like that that have glycerol in them. It's nice on the skin, and again, very benign. So, right, so that's glycerol. So a triacyl glycerol or a triglyceride, let's put it over here, would just be a triester of glycerol with 3 fatty acid molecules. I'm just going to put R here for the, whoops, I forgot my oxygen. I wouldn't have it an ester, I would have it a ketone. There we go, that's better. So that would be the structure of a typical triglyceride or triacylglycerol. This is, my understanding is this is how fat molecules are most often stored in the body, or stored, or oh, what's the word I'm looking for? Moved around, transported is probably a better word. So these 3 R groups can be either the same or different, doesn't really matter. But you can see that we have fatty acid portions. This is the carboxylic acid portion, and all we've done is we've removed water 3 times and made ester functional groups. That reaction also we'll talk about more in a later chapter. We'll talk about esterifying carboxylic acids. That will come in a later chapter. But this is what a typical triglyceride or triacylglycerol looks like. And again, you probably don't have to go to the doctor to get your blood drawn quite as much as I do. When you get old and decrepit like me, you need to do that every year, and for good reason. There's lots of things that can be detected early based on things showing up in the blood. But one of the things they always do, and you might have had this done in the past, is they check out your basically your metabolism. They want to know how much glucose is in your blood. They want to know how much triglyceride is in your blood. And this is why you need to have your blood test taken fasting, because if you go eat 5 cheeseburgers and then get your blood drawn, it's going to be loaded with triglycerides, and you won't get an accurate reading because you'll be in the process of digesting them. So, but they want to know basically what your fasting level of those things is. So that's why you have to fast. And there's a certain acceptable level of triglycerides. There's a certain acceptable level of cholesterol. There's a certain acceptable level of glucose, which is the form sugar is usually transported in. We'll talk about glucose when we get to our chapter in carbohydrates. But these are the very things that they're testing for when they test for triglycerides in your blood. They're essentially triesters of glycerol with 3 fatty acid molecules. And that leaves us in a good place. There are certainly other derivatives of triglycerides that we'll get to, your phosphatidates and phospholipids. I want to leave those for Monday, since we're not in any particularly huge rush here. Good. So and I hate being the guy that erases everything. I probably told you about a math professor I had when I was in college who was literally eraser in one hand and chalk in the other. I called him Fast Eddie, but that's another, not to his face, of course, but that's another story. I don't want to be that guy, but at least you can always watch the video since we are recording if there's anything that you missed. Maybe there's something I can fit a little more in. Oh, why squish it? Why squish it? Let's get a clean slate. So I also today want to talk about soaps and detergents in general, because they're closely related to triglycerides, actually. In fact, they're made from triglycerides. But soaps are made by taking a typical triglyceride. So I'll just draw this again. And what we're going to do to this triglyceride, again, these R groups can be either the same or different, it doesn't matter. But what we're going to do to the triglyceride is something called hydrolyzing it, or another word is saponifying it. It actually comes from the very same root that means soap. I'm I don't know if that's Latin or Greek, I should, but it's one of the two. Anyway, this too is a reaction that we'll learn about more in detail in a later chapter. But so what we're going to do is treat this with aqueous sodium hydroxide or potassium hydroxide, either one, and also water. And what we will get out of that is, first of all, the glycerol back. And we will also get 3 of these fatty acid carboxylate ions. So you get 3 of these ions with it. And that's what you'll find in the soap. Again, remember, R is going to be an arbitrarily long chain. So that's what soaps look like. They are somewhat reminiscent of the phospholipids that you find in cell membranes also. So soaps have some structural similarity to that, I would say. But you get glycerol and 3 of these. The oxygen in here comes from the hydroxide ion, actually. So, and it's this mixture of things together, plus, of course, you would also get either a sodium ion or 3 sodium ions or 3 potassium ions. Your book, by the way, I'm not a huge fan, likes to put the sodium or potassium right next to the oxygen. I'm not a fan because it looks like they're bonded, and they're not. It's an ionic compound. It's a salt, just like sodium chloride. So please watch out for that. I see that in a lot of textbooks, and it kind of sets my teeth on edge. But in any case, it's this mixture of carboxylates that is what we mean by a soap. It's essentially sodium or potassium carboxylate ions that come from the alkaline hydrolysis, or if you will, the saponification. This is called saponification, S-A-P-O-N-I-F-I-C-A-T-I-O-N. That word turned out to be a lot longer than I thought. So that's called saponification or alkaline hydrolysis. And we'll learn about that reaction in a later chapter in a more general context. But after that process, it frees up the glycerol, which that's your glycerol. And you also get 3 of these fatty acid carboxylate molecules. And it's that mixture of sodium or potassium carboxylate ions that you will find in a soap. I think in general, you'll find that sodium carboxylates of this type are what you'll find in solid soaps, and potassium carboxylates are what you'll find in liquid soaps. So you know about those two. You go and you get things in the pump bottles. Those are liquid soaps. So this method or technology of making soap is thousands of years old. You can imagine how early on, how many lives must have been saved just by discovering how to make soap, and it's not that hard to do. And you might very well have done it also, even in high school chemistry lab. I would not be shocked. They often will have the kids make soap. And all you do is you take Crisco and you add some aqueous sodium hydroxide and you heat it for a while. And what you'll get out the soap that you get from the sodium carboxylates, or you might use potassium hydroxide and make the potassium salt and get a liquid soap. Oftentimes, I believe they'll even leave the glycerol in there, since, as I've said, it's quite nice on the skin and more or less completely benign. So there's no point taking it out. I think they often leave the glycerol in soaps. Or, I mean, there's ways of taking it out also. It probably depends on the type of soap. But that's basically how soaps are made. And as I said, this method of making soap has been known for hundreds and thousands of years. It doesn't require anything newfangled at all. It just requires some animal fat and a fire. You do need a fire. And you do need to get your hands on either sodium hydroxide or potassium hydroxide, which in the olden days used to be called respectively caustic soda or caustic potash. So there are ways of making that too. They're actually un poco dangerous. I would be careful with anything but very dilute solutions of base. It's certainly bad for your eyes. Definitely keep it away from your skin. But in very dilute solutions, don't go drinking it. But that'd be bad. But as long as you're careful with it, you can use it to make soap. So that's one thing. That's fine. Yeah, we'll leave phospholipids until later. What about, but there are some problems. What about some problems with soaps? First of all, one problem with soaps is that they can generate alkali in aqueous solution. I'll here indulge me by putting the sodium ion very far away from it. It will make my, as I like to say, it'll warm my tiny, stony, cold, dark, evil organic chemist's heart if you do that. I will really appreciate that. Oh, yes, question. Oh, we're getting to it. There are a few problems. One of which is that, oh no, you're right, I did actually say it, didn't I? It generates, well, I can even write that down. Soaps generate alkali or generate base in, can I go aqueous solution like this? H2O, and you will wind up, there's an equilibrium involved, of course, but you will wind up getting some of the free fatty acid plus OH minus in some concentration, O plus Na plus, I guess. So that's still there also, if you want to be picky and have a balanced equation. OWL likes you to make separate sketchers with ions in them. It's kind of a pain. But do be sure to read the directions. Normally, we don't focus on those inorganic side products. But that's one problem, because the hydroxide ion base is bad for clothes. It can decompose fibers in clothes. So that's a problem. That's one problem. Another problem is that, oh, and let's see. I just want to make sure I get this right. You'd say, well, just add some acid. That doesn't work, though. Adding acid to plan ahead for getting base and neutralize the base, that doesn't work because it only generates insoluble. And we want our soaps to be soluble in water, right? But it generates insoluble fatty acids. Oops. That's not part of the same sentence. There we go. So for instance, you'd say, well, I'll just take my soap and I'll add some acid like HCl. That will prevent the base from being formed, the hydroxide, which will prevent that from damaging clothes. And not that HCl couldn't also damage clothes, but we'll just work with it for a while. That's not going to be any better, because although you certainly will stop hydroxide from being generated, all that happens then is you get the free acid, the fatty acid back, which is, and I guess you would get sodium chloride. So this is insoluble. You get these fatty acids back from the acid-base reaction, and those are insoluble. You get like a bathtub ring or a scum or a ring on the clothes. That's not going to work. And there's a third problem that's also pretty bad with these older kinds of soaps that we've had for hundreds and thousands of years, which is they act very poorly with metal cations, such as you will find in hard water. Now, you may have hard water, you may have soft water, but at some point in your life, you're going to run into hard water. And let's see, form. It's one of the worst Fs I've ever drawn. I almost need an F in chat for that F. Form insoluble salts with metal ions in hard water. And these metal ions include things like calcium, iron 3, copper, you know, just whatever you can get off of the pipes, I suppose. But just to show how that works, if we start out with oh, you know, there's a pencil here. You'll indulge me, I just realized there was a mistake in my lecture notes. I will, of course, write it correctly for you. they will react if you had, say, 2 of these carboxylate ions, Na+, and that managed to find, say, a calcium ion. I'm just going to use calcium as an example. I could have used any of these other metal ions that you commonly find in hard water. What you will get then, I don't think there's even much of a, actually, I don't think this is an equilibrium either. Make me feel better if you make that just a regular reaction arrow. That's going to go to completion. This will go to completion also. But what you wind up getting is the calcium carboxylate with 2 of these carboxylate anions plus the calcium 2+ ion, and then you will also get 2 sodium ions. And this is insoluble. In the olden days, they would complain about bathtub ring, and that almost always would happen in households with hard water that have all of these metal ions in them, and they would then precipitate with the carboxylate ions that you find in soaps and make these insoluble, sometimes colored rings around the bathtub. So that's a problem. And what we need is a way to solve this problem. And again, I'm kind of running out of room though. The solution though is to use synthetic detergents. Also known as Syndets, S-Y-N-D-E-T. Again, this is the new material that I literally learned from reading your textbook. So, so these are significant problems with traditional soaps of the type that we've had around for hundreds and thousands of years. And these newer detergents, and you'll find these things, I think, in your shampoos. I think you'll also find them even in laundry detergent, things like that. There's a certain particular way of making them that I don't think is outside of our reach to understand. So again, sorry for erasing, but I've filled the whole thing up. So what we start with, making a Syndet. What we start with is, once again, some triacylglycerol or triglyceride. Wait a minute. That doesn't look right. There we go. That's more like it. That's an oxygen, sorry. So we start with a triglyceride, and what we do first, rather than just hydrolyzing it or saponifying it, we reduce it. We add an excess of hydrogen gas. We need at least 3 mole equivalents. So H2, hydrogen gas, and copper chromite of all things. I keep meaning to look up the formula of copper chromite, and I don't know if it's copper 1 or copper 2, but I don't think I really care if you memorize it anyway. So we'll just stick with the name, copper chromite. So what that's going to do is give us our glycerol back. So you cleave off the glycerol, and you will also get 3 of these long chain alcohols. So they're no longer carboxylic acids. So let me get a color over here. This carbon over here used to be the carbonyl carbons. That's that carbon. It's now reduced to a CH2. So you get these long chain alcohols by this reduction reaction. And this is, of course, done industrially on huge, enormous scales, as you can imagine. And so the next step, oops, I don't want red anymore. Next step is we take one of these alcohol molecules, well, many alcohol molecules, of course, and we treat it with our old friend sulfuric acid, H2SO4. And from that, you get the alkyl sulfate. which looks like this. And you also do get a molecule of water out at the end. We're not really concerned about that. We're concerned about this portion. And so then we take that, the third and final step is we take this alkyl sulfate, which is now a very strong acid. It's almost like sulfuric acid. And we're going to add some base, like sodium hydroxide. And you will get the sodium salt of the alkyl sulfate. Na+, and of course you will also get a water molecule. And it's this species here, that's your Syndet, that's your synthetic detergent. And these things are a good deal more soluble in water. Sulfates in general are extremely soluble, but they're quite soluble in water, and so you don't have a problem with anything crashing out of solution and making scums or rings. They're even soluble if they come in contact with all of those nasty metal ions that we talked about on the previous page. So your calcium, salt, and so forth will all still be soluble. So that's the great strength of these Syndets. And you'll find them listed in the ingredients of your shampoo or your laundry detergent or like that. I think that's where you'll mainly find these things. But they're much more advanced than the old soaps, and they don't have any of the problems that we went over on the previous page. So yeah, I think that's about it. I suppose there's not going to be a huge hue and cry if I let you go 7 minutes early on a Friday. But that's all I wanted to cover today. We can leave the rest for Monday. There's no need to rush. So have a great weekend. We'll see you on Monday.